Okay, let's get started. A very good afternoon to everyone. Welcome to this week's Coloquio. It will be given by our own Sundar Srinivasan. So Sundar received his master's degree in physics from the Indian Institute of Science in Bangalore, India. Then he moved to the Johns Hopkins University in the States, where he got his PhD. And then he hopped over to Paris for his first postdoctoral fellowship at the Institute of Astrophysics, and then moved to Taiwan at the Institute of Astronomy and Academia Sinica for his second postdoctoral fellowship, after which he landed here in 2018 and assumed the faculty position at the Institute. So Sundar's research focuses on the production and evolution of dust around evolved stars in our Milky Way and nearby galaxies. He applies advanced statistical methods to large observational databases in order to construct models of the gas and dust from evolved stars. He's also interested in statistical methods and machine learning. If you don't know, he's the go-to guy if you want to know anything about statistical methods and machine learning, at least for me. And he's very happy to discuss if you have any projects or problems with machine learning. He'll be very excited to discuss these things with you. Sundar also organizes the meetings of the data analysis working group at our institute, which are called DALI meetings in short. And he also teaches optional courses on astrophysics. So today he'll tell us more about this nearby evolved stars survey. Thank you, Sundar.
Thanks, Amandeep. Sorry about the delay. We had some technical issues. That happens every other week. This is, I'm just going to summarize for you results from a paper that is, so Sophia Wallström, who was one of the fellow postdocs in Taiwan with me, was working on this paper. She submitted the first version back in, well, I guess she quit astronomy first, because it happens to a lot of us, in June last year. But just before she was doing that, she had made the first version of the paper ready to submit. Then I took over. So I've been taking care of this paper since then. We just got a referee report, which was very favorable a couple of months ago. And yesterday, I just sent back the referee response. So I think this should be accepted. Well, I was hoping for an email this morning, but it should be accepted soon. So Sophia was the first author of this paper. She was at KU Leuven when she quit. Peter Scicluna is the PI of the NESS survey that I'll tell you about a little bit. Some of my close co-workers on these projects have been Alfonso, who's unfortunately had to go to Mexico City today, Ian McDonald, who's in Manchester, and then Alfonso and I co-supervised a couple of students from Ciudad Juarez that I'll tell you a little bit about what they've done as well related to this project. Okay. So why do we need to study HB stars? You may have seen this slide or these kinds of slides in my previous talks. This is the life cycle of dust and gas in a very nice graphic here. So you start out in a star-forming nebula. Depending on the progenitor mass, you either go the massive star route, where in a few million years you turn into a massive star, a red supergiant, and then you have a supernova. And then you recycle material out to the icing. This takes maybe 10 million years or so. If you're a sun-like star instead, mass is between 0.8 to 8 times the sun, then you turn into a red giant first, takes billions of years, and then an asymptotic giant here, which is the stage that I'm going to talk about. That's why it's missing from this graphic. And then eventually a planetary nebula and a white dwarf. But that missing piece is where most of the action happens. The idea is that because there's sunlight, that means that they are numerous compared to massive stars. So HB stars are important because one of the things they have is they have, of course, nucleosynthesis, but the third dredge up mechanism, which drags this material, this nucleosynthetic product material, out to the surface where other stuff happens to it. Of course, the most important product of this nucleosynthesis in HB stars is 12 carbon. There are a lot of other light elements as well as some of the transition elements. Mass loss. So HB stars lose up to about 80% of their initial mass while they're in this relatively short phase. in the form of very slow or 10 kilometers per second stellar winds. Because of this, they are involved in the recycling of material to the ISM and therefore have a profound effect on galactic chemical evolution as well. Because again, like I said, there are many of them. The mass loss is extremely dusty. So AGB stars are among the primary producers of dust, solid material, and of course the dust drives this mass loss, is radiatively driven. So again, and we need dust for various things. I think there are enough people in the audience here telling you why dust is important to the ISM. So I'm not going to do that. These sources, again, because they're numerous and because they produce a lot of dust, they are dominant stellar sources of dust in the in present-day galaxies. And this, enough work has been done on this in the mid-infrared to demonstrate that this is the case. So, okay, this is a very, very busy diagram. We're going to spend a lot of time on all of it. This is kind of a cartoon of the structure of an AGB star and its stellar shell. And kind of what are some of the things you can do using multi-wavelength instruments. So AGB stars have an inert core of carbon, oxygen, and hydrogen, around which you have these two concentric shells of helium and hydrogen. That's where most of the action is going on during the AGB phase. Every once in a while, the helium shell flashes, the hydrogen shell is constantly burning, and the intershell region here has nucleosynthetic material, which is brought up using so this is convective mixing happening in the rest of the envelope of the star, and that recycles this material out to the surface. Interesting things happen on the surface because of thermal pulses. There's pulsation as well of these. AGB stars are long period variables. They have periods anywhere from about 30 days to about 3,000 days or so. Their surfaces pulsate with relatively high amplitudes as well. And there's interesting chemistry happening on the surface as well. Because they're bringing up 12 carbon, the carbon to oxygen atomic ratio slowly rises. Initially, it is oxygen rich, the surface, so all the molecules are oxygen rich. So this one here, all the molecules are oxygen rich. But eventually, with enough dredge-up events, the chemistry turns carbon rich, and therefore you have carbon rich molecules. And these molecules, as they, because of pulsation, they get levitated to cooler regions where they start forming solid materials, and that is dust. So you can have, if it's oxygen rich, you can have silicates, magnesium, aluminum oxides, iron oxides, and if it's carbon rich, you can have things like amorphous carbon, graphite, and carbon. Further out from the star, there's this is the acceleration region where the velocity starts out very small and then gets to approximately the terminal velocity of the wind, and then a stable outflow is driven from about 10 times the stellar radius, and then out at the edge here. So we've kind of sort of jumped here from the interior to the exterior, 10,000 times the stellar radius, where interesting interactions happen with the AGB. That part, but there's over the waves, there are many things that you can do. So with the optical, you can actually look at what's happening very close to the surface of the star. Because there are so many, because the temperatures are relatively cold, the molecular species are just abundant, and that means that there's a lot of line line. The variability means that the obscuration from these molecular bands can be super high as well, which means for the most interesting AGB stars, you can't really use the optical because they're basically very faint in there. So we start with the near infrared. You can look at absorption bands, atoms, molecules. You can look at variability as well, so you still get to see what's happening very close to the surface with this wavelength. With the submillimeter radio, you can actually, if you have, you can look at hot gas in the chromosphere. You can look at what's happening in the dynamic atmosphere. With radio, with masers, so silicon monoxide masers, for example, you can look at how dust precursors like the SiO molecule, how they are interacting and helping produce the dust. With the mid-infrared, you can look at the warm dust that is very close to the dust formation zones, somewhere here, maybe 3 to 10 times the stellar radius. With far infrared, you can look at older dust that was produced earlier and has moved out with the subliminal radio again. You can look at very cold dust, but also you can look at CO rotational lines, low J rotational lines. So that's what this talk is going to be about. We are planning for PRIMA, and so one of the things PRIMA can do is it can give you constraints on the integrated intensities of high JCO lines. So as the angular momentum increases, you start probing regions closer and closer to the dust formation zone of the star. And so if you look at J equals 6 to 5 and higher, you can actually probe what's happening in the acceleration zone. So that's kind of exciting if we can do that, get constrained. Right now, we have no instrument that can do that. We have predictions, but we have no instruments that can verify these predictions. So this will be nice.
Good questions on that. Yeah. Does that picture care about how fast you're moving?
No. There's usually with these stars, if you're talking mostly about the stars that are below about 5 solar masses or so, we don't consider rotations.
Or this is for specifically for a non-rotating star.
Yeah. Okay, so where have we studied AGB stars? Well, why do we do it right next to us? Right. The problem is there's foreground exchange. We're sitting in the dust disk. The distances are therefore uncertain. If the distances are uncertain, that means the mass loss rates are uncertain, the luminosity is uncertain. Basically can't do anything. And there are various effects happening. So the AGB stars themselves, even if you ignore if you somehow account for the interstellar dust, there is still a problem that the AGB stars produce dust. So there's circumstellar dust, which is also causing issues. There's pulsation, which dynamically changes the surface. So how do you define where the surface is? Well, that keeps changing as well. There's convection, which again complicates how you define where the surface is. There's dust obscuration, which means you can't really probe regions very close to the surface. And because of this, parallaxes are also imprecise. I showed this number here in Heidelberg in 2022, and they were like, wait, what? Really? That's 40%? Yeah. You go to the Gaia DR3 parallax archive and download this data. And yes, the nearest, well, these two are the nearest AGB stars, about 100 parsec or so. And the parallax uncertainty in Gaia is 40%.
Why is parallax with Gaia 40% and with the Parcus 10%?
Just different stars. It's not the same star though.
Yeah. Different stars.
So
the same distance, more or less, right?
Yes. But it depends. I think like the physics happening here. This is a much more extreme AGB star. So it has much more complicated stuff happening to it than Mira. Mira is also a Mira variable, but it's the things that are happening here are much more complicated. So yeah, that's the other problem is that even if you have things at the same distance in comparable luminosities, they have different histories and different mechanisms happening. So we need a large sample. So that's a good motivation for that. Yeah. So anyway, this is one of the problems, and this won't be fixed with Gaia DR4 either. It will be improved, but really what we need is a near-infrared version of Gaia, which is long. So we need other techniques to do this. In the meantime, what can we do? Well, we can look at compact populations, the galactic bulge. We know approximately where it is, right? We can look at stars just there. And people have done that. One of the issues with the galactic bulge is there's way more dust obscuration there. So again, you have to be taking into account all of that stuff. You can look at targeted samples, things where you know these things are AGB stars. You have an approximate idea of the luminosity. You can look at those, and people have done that as well. Or you can look at only one kind of AGB star. You can look at only the stars that have carbon in them. You can also have larger samples if the telescope people are generous enough, and if you're ambitious enough, you can say, hey, look, I have this large sample. I don't know if we're going to detect all of them, but will you give us some time? And sometimes they're like, sure. So you can have, and there are many studies that have low detection rates, but these are the studies that are actually doing the kind of frontier research, looking at, hey, look, we might accidentally end up discovering something rather than what is typical in AGB research at long wavelengths, which is, I'm sorry, this source has not been studied 15 times before, so you can't get time for it. There is a lot of stochasticity, of course, when you look at small samples, or if you look at targeted samples, or larger samples with low detection rates. So there's all of these issues you can have with this. What we really need is a volume complete sample large enough that you can get statistically robust results out of it that give you the span of all the possible observable parameters, measurable parameters. So in order for that, and also this has not been done for the solar neighborhood in a long, long time. In the late 80s, early 90s, people had data of this, but again, it was not homogeneous, it was not volume complete. Again, the distances were extremely uncertain. So there comes the nearby evolved stars survey. NESS is a survey of about, I think it's 851 nearby evolved star candidates. We started out saying their distances are within 3 kiloparsecs. We have updated their distance estimates. So I think most of them are within 5 kiloparsec, and about 75 to 80% of them are within 3 kiloparsec. Of these, 781 are highly reliable agents. So these things in selection, did not only consider confirmed. So of course, there's quite a bit of contamination here as well. But 781 confirmed AGB stars, which are, you have not only the dustiest ones, but also the ones that are just entering kind of the dust losing agent phase. So it's important to also observe those, because that tells you where exactly dusty mass loss begins at what stage. There's also a partially overlapping sample of 507 stars within 300 parsecs. It's called a 300 PC sample for us. This consists of, this consists of stars that are just at the luminosity limit, below which you have RGB and not AGB. So this luminosity limit is about 1,200 solar or so, and anything above that and less than what the rest of the sample is what this so we haven't done very much with this yet, but because they're nearby, data for them exists in a lot of archival studies. Okay, so what papers have been published and what are in prep? The overview paper, Peter Shiklona, PI, was published in 2022. It has a summary of the JCMT continuum data and talks about what other projects have been planned, and it talks about there's a subsample of the 850 sources that was also targeted for mapping studies with JCMT. A paper is summarizing the catalog, where we've combined not just the JCMT data, but all the archival information from the optical up to the far infrared to produce very well sampled SEDs. They look beautiful. Was also published earlier this year. And right now, of course, we're talking about this paper, the JCMT heterodyne data. There is also, this one also is going to be resubmitted soon. Kei Yamada in Japan is leading a paper summarizing the Nobayama radio data. And then a couple of papers. This one, again, Manali needs to graduate like yesterday. So I think she is going to submit this soon. And Alfonso hopes to, by the end of this year, at least have a first draft ready of this work, which I'll tell you a little bit about. We also have a bunch of other things in progress. I'll tell you a little bit about the LMT data. We have data from VLA, which has just been sitting there because we haven't had the time to look at it. Over the past year and a half, we thanks to Coloquio at IRyA, we discovered that there is this optical telescope sitting in India where it's not as competitive as other facilities. So we went to hey, can we collaborate on something? So we have optical spectra of some of these sources, and we will be getting more, which will help again look at the pulsation properties. So it's a very complex data set. It's about over almost 800 stars with data from the optical all the way up to radio wavelengths. So it means that when I showed you that figure before, it means we can actually probe all the physical scales in the circumstellar shell of the AGB star, which means we can find out, we can probe the mass loss history, not just the current mass loss rate, but the mass loss history of the AGB star. So there are a couple of ongoing, this one's finished, but there are a couple of studies that are very, very recent also that are either, so they have higher resolution, but fewer stars. This one is very, very targeted. There's only 14 oxygen-rich AGB stars in the sample. This one has more stars with lower resolution. But there are also ongoing things that are very good complements to what NESS is doing. Okay, fine. Let's get to the meat of this thing. I'll tell you about the results from our paper, and then at the end, just advertise a few other things. Okay, so this is first summarizing what the NESS sample looks like. So the original NESS sample was selected just from the IRAS point source catalog, just because we want to select dusty sources. So we picked a catalog that has dusty objects in it. From this original sample, then we did a bunch of color cuts and SED fits and stuff to figure out which things we think are likely, possibly stars. And we then said, okay, can we compile distances for these objects? And so we went to Gaia, went to Parcos, went to whatever else we could find. The ideal thing would be if they had Maser parallaxes, because those are the most precise things. And SIO Maser parallaxes is one of the things we'd like to do with VLA. But unfortunately, for this nearby sample, again, I think of the 780 objects, 850 objects, we have Maser parallaxes for 13. So we counted that. But the rest of them, geometric parallaxes from Gaia and Parcos as well. You know, keeping in mind that these are not going to be as precise because of various issues. You could also, if you compile the SED of each object, then calculate the volumetric flux, and then assume an average luminosity for an AGB star, and then use that to calculate the luminosity distance. We did that as well. We went one step further than what was done in the 90s, where they said, okay, all AGB stars are 10 to the 4 L-sun. We said, no, well, we have the luminosity function of AGB stars from the magellanic clouds. Very well done. Why don't we take that? So take an average as well as an uncertainty around it. So it turns out to be very generous. We can say the average luminosity of an AGB star is 5800 plus or minus 50%. So a 50% uncertainty of luminosity translates to a 25% uncertainty of the distance. Seems big, but actually it's comparable to the kind of precision you get from parallaxes, geometric parallaxes. So the way we did it is we said, if the distance uncertainty from luminosity is less than that from the parallax, then you accept that. And just by doing that, the majority of the NESS sample has luminosity distances, right? Okay, then we use these SEDs, fit them with AGB models to produce dust production rate estimates as well. And using that, so we have distances and DPRs, then we have this diagram, which has, so the 4 major colors in the background, so the 4 different distance DPR tiers. This is a wedding cake distribution of our sample. And on top of that, you see some special sources. These sources, the purple triangles, have been selected by hand. And they're basically known sources that are nearby that we somehow missed when we're doing the IRAS-BSC selection. But also they're known AGBs without a lot of dust. So it's important to just sample this particular tier, which, by the way, in most surveys, because they target bright AGB stars, infrared bright AGB stars, they are not sampling this region very well. They're going for the champions, people who have the maximum mass loss rates, maximum DPRs. So that means that NESS is doing much better than other surveys as far as the lowest dust production rate sources goes. This is a box plot showing the distribution of dust production rates in these 5 tiers. So you can see that the ones that we selected based on our semi-automatic selection, that the dust production rate increases on average. The very low sources, these purple triangles, are selected by hand, so there's not really a trend. Okay, that was 2022. And then Ian McDonald did a much better automated SED fitting plus distance compilation strategy, by using which, and then very, very carefully judging what the distance estimates were, he was able to actually update the distances. So this whole thing shifts slightly, and you kind of, if these are the old boundaries here, And what's happened is basically he ended up rejecting quite a few of these sources. So these are either much further out or not AGB stars. That's what these, so the 70 sources that, from going from 850 to about 780 or so, a large fraction of that happens to be just checking that, hey, are these sources, oh no, this is a YSO. Or, hey, sorry, this distance turns out it's not 3 kiloparsec, it's 10 kiloparsec. So that was done, this is from what published earlier this year. And then the paper that I'm talking about here is the JCMT heterodyne data. So again, in gray in the background, you see basically this entire sample. And the colors are the ones that were actually targeted by the JCMT heterodyne instrument. So, of course, the colors here represent the various tiers, but also some pluses here are just the carbon-rich stars. So you can see that the carbon-rich stars are typically just in these 2 tiers, whereas you have many oxygen-rich stars that are at low mass clusters. This again is consistent with the way we think AGB evolution works. So this we have a total of about 493, I think, 485. I think it's probably between 485 and 493 sources with detections, of which 259 are detected 2 to 1 and 428 in 3 to 2. All right, detection statistics. Actually, we're doing either as good or better than most other literature samples. The fraction of sources detected is between 75 and 80% in either line. And of the 490-ish sources, we had 59 that had no CO observations previously. And the 3 highest tiers, so this is intermediate, high, and extreme. In these tiers, this is carbon rich, this is oxygen rich. The detection rates are relatively comparable, which means that we're not biased by source type, which is what was one of the motivations for going for this kind of survey. Okay, so we have CO data, so I'll show you some line profiles. This is what the CO spectrum look like. Overall, this is visual inspection. We separated these into 3 broad types. There are special things happening in these things as well. 82% of the sample, predominant sample, has this soft parabola shape. The spectra have the soft parabola shape. There are 11 sources that have this kind of double wind thing happening. Many different kinds of morphologies, but yes, there's multiple wind components in them. And then there are a handful, I forget how many, maybe a dozen or so, that are asymmetric, and they have wings. So these kinds of sources, these special outliers, they're well known. It's not surprising, they're well known in CO data. The deviation from the soft parabola can be attributed to things like companions, non-spherical distributions. If you have an inclined disk, a bipolar outflow, or some sort of equatorial enhancement. And this happens in more evolved AGB stars, or especially when you have companions. So this is a known thing. But let's focus on the soft parabolas. So soft parabola profiles are seen in spherically symmetric AGB stars, which have constant velocities. So there's not a lot of wind. Basically, you're probing the entire region where the wind has finished accelerating and has a constant velocity. So it's a known thing. This is good because then we can use one-dimensional single-channel models to model these as a starting point. This is good because, and that's most of the sample. So hopefully, and this is in progress right now that we're working on, we're trying to figure out a consistent, automated way to model the entire sample radiantly fast. And the deviations are important again because then, of course, we will have to figure out how to modify them in a consistent fashion, the 1D models, in order to figure these out. Of course, you can do, source by source modeling, which is what is done in the literature. It's just we are looking for reproducible. So this is a profile that's called the soft parabola. So you have this the velocity relative to the LSR in terms of the expansion velocity, which is right here, and 1 minus this squared raised to beta over 2, where beta is the shape parameter of this profile. So you can, depending on the value of beta, you can go from something like a double bond profile all the way out to a soft parabola, and intermediate, you can go to a rectangular profile as well. So we fit these soft parameters, we estimate the peak intensity and also the expansion as well for the entire sample. And then once you have the integrated intensities, which you can just get by, so just from the data itself, you get the integrated intensities and the velocities as well. There is an empirical formula that you can use to calculate the gas mass loss rate. The correct way to do this, systematic way to do this would be radiative transfer, but like I said, we're on our way there. In the meantime, there's this equation derived from 20 stars. So of course, there's significant systematic uncertainties here. These coefficients, this one, they're different for different transitions, and there's a huge uncertainty. The mass loss rates end up being, the uncertainties end up being order of magnitude or more. So with the caveat that yes, we have mass loss rates, but factor of 10 issue, and the equation is not reliable for high mass loss rates either. But it's the best we can do without really transforming. There's a lot of upper limits to this as well. So first thing we'll do is let's compare it to what people have done before. Let's compare our empirical mass loss rates with what other people have, and it's not pretty bad. The velocities which come from soft parabola fitting, they are much better constrained compared to the literature. So the agreement is much nicer. Here the spread is higher because again, a lot of this one order of magnitude spread is due to the uncertainties we have in the empirical mass loss rate.
Is this kind of normality between oxygen and carbon rich real in the mass loss rate?
Which bimodality? You talk about the fact that the carbon-rich stars have high mass. Yes. So the way AGP evolution works is that you start out oxygen-rich on the surface, right, regardless of your initial mass, and then the dredge-up events depending on your mass. So if your mass is less than about 2 solar masses, there's not enough dredge-up. You always stay oxygen-rich. So you have a low-mass oxygen-rich sample, this one, and then if your masses are between 1 and 4 solar mass, then eventually you become carbon rich, right? So that's these guys here. And then if your mass is more than 4, the hot bottom burning destroys 12 carbon because before it can get to the surface. So they are massive oxygen rich. And then this bimodality is a real, yes. That's why in the sample as well, the carbon rich sources were only in the 2 intermediate years. Yeah, so the idea is that NESS reproduces the mass loss rates that other people have, but we have this low mass loss rate sample that other surveys don't. Okay, so then one of the other things you can do is look at the isotopic ratio of 12 carbon to 13 carbon. Why would you do that? Well, 12 carbon is produced during the third dredge-up, which means that the isotopic ratio is then a measure, some sort of proxy for the evolutionary stage longitude. In principle, yes. So, in some way, the apparently models say that the ratio starts out at about a few at the start of the AGB, and then with subsequent third dredge-up event, you can increase this all the way up to 100, a few hundreds. Of course, a massive, related to the question Dr. just asked, massive AGB stars have this competing process that destroys the 12 carbon before it gets to the surface. So in those cases, you might even expect a reduction in the 12-30 ratio instance. At least for these ones, because there is an evolutionary thing, you would expect that the isotopic ratio should correlate with mass loss. As the AGB star evolves, the 12 to 30 ratio should increase, but also mass loss rate increases, because that's again part of the AGB evolution. So do we see that? So this is a plot of the ratio versus the mass loss rate. And in fact, if you squint your eyes, you see an anti-correlation there. What is happening there? So, okay, it looks like the more of all sources. So the problem is, of course, the 12 carbon, the 12 CO line can be optically thick, these sources. The 13 CO not much, because there's not a lot of 13 CO. But 12 CO can be optically thick, which means that you won't probe all of the 12 CO that's there in the shell, which means it's an underestimate for how much 12 CO there is. Therefore, this is an underestimate for the 12 to 30 ratio as well. This is in fact a problem for most of the sample. Yeah.
Why the ratio up and the hot burning affects 12C and not 13C?
It has to do with the nucleosynthesis production rates of 12 and 13. So 13C is not an S process element, so S process isotope. So it's generated in a larger fraction. It's generated massive stars rather than so. Intermediate mass AGB stars produce more 12C. In the on the AGB, there's 30C production, I think, in the RGB. I'm not sure. Yeah, but in the AGB, this is the primary. So yeah, unfortunately, most of our sample is optically thick. There are 10 sources which have at least one optically thick thin CO line. So those are these things here. But yeah, you can't really get anything out of them either because it's quite significant. So okay, this still needs work. We'll have to do radiative transfer modeling. We can't do anything other than that. We can look at, okay, is there a correlation between the mass loss rate and the dust production? Why should there be a correlation? Well, dusty mass loss, the way the mechanism works is you first produce dust near the surface of the star. This dust gets a kick from the radiation pressure, introduces an acceleration in the dust. The dust then has frictional coupling with the gas and carries the gas along with it. So dusty mass loss, this is the way it works. You first produce dust, then you have radiation pressure, and then you interact with the gas, and that drags the gas along. So we hope that there should be a correlation, and yeah, if you ignore the fact that, so there are a lot of upper limits here in the mass loss rate, but you can incorporate that. So this is not just some by eye fit, right? This is an MCMC that incorporates all of these upper limits into it. So this is real. So despite the fact that there is an order of magnitude or more spread in this, the spread in the trend is not as large. So it's very well constrained. And again, this is not, oh, let's ignore everything else. No, it has incorporated all of the data into the fit, right? Using an MCMC. So the mass loss rate seems to increase with dust production rate up to a certain point, beyond which it seems to kind of flatten. So there's a saturation of a mass loss rate at about a few times 10 to the minus 6 solar masses. And this break that you have here, that actually coincides this at a few times 10 to the minus 8 dust production, a few times 10 to the minus 6 mass loss rate. It coincides with the break in the distributions of the dust production rate and mass loss rate as well. And that's a real thing. We verified this in the sample as well. It's not just a selection effect because we have selected everything that's there. They are very dusty, therefore they're very bright in the infrared, so you can't miss them, right? So we haven't accidentally missed something here. So this is a real thing, and so it could be possibly an evolutionary effect. So one of the things that happens at the highest mass loss rates is at some point, the mass loss rates turn off. So we might be looking at what is called the superwind phase, AGB stars, where the mass loss rate reaches about a maximum where there's no longer any material left to drive mass loss. Once you have the mass loss rate and the dust production rate, the ratio of those two will give you the mass ratio of gas to dust, as in how much gas is required to produce a certain amount of dust, if you look at it that way. We can calculate these ratios, and so you have for O-rich AGB stars and C-rich AGB stars, the ratio there. The median here is about 150, sorry, it's actually 300 or so for, let's see, what's it like here? Yeah, 250. This is a 68% confidence interval around it. So it's a generous confidence interval for the dust to gas to dust ratios. The carbon-rich sources seem to have somewhat higher gas to dust ratios. One reason this could be possible is carbon dust is more efficient at interacting with radiation, so you need less of it in order to produce the same mass loss. And of course, there are also model assumptions that go into this. One reason we know is that the choice of amorphous carbon optical constants significantly changes what the dust production rate is. If your dust production rate is lower, that means the gas to dust ratio is higher. And we know definitely Martin uses a different set of optical constant from us. We know there is a factor of 10 difference. Okay, so we know that the mass loss rate and dust production rate are correlated, but the slope, which I showed you in the back, doesn't matter, is less than 1. So it's sublinear, this relationship, but they're correlated. If MLR and DPR are correlated, then the ratio, yeah, it's derived from the MLR and the DPR. So of course it should have some correlation with the MLR and the DPR, right? That's what you think. But then we find that the mass loss rate and the gas to ratio are not, there's no significant correlation, which is weird. But it gets weirder. There is a weak correlation between the dust production rate and the gas to ratio. So this is a large enough sample that weak correlation, it's weak, but it's there, right? So this is very strange. Why should it correlate with one of them but not with the other one? And so we think, we say, what if what's happening is this? So the way that dust-driven mass loss works is you need radiation pressure first to give a momentum kick to the dust. The more dust there is, the more momentum change there is. So as the AGB evolves, there's more dust production, there's more dust, so there's more momentum from the radiation. But then how is this momentum distributed to the gas, right? It can either go into increasing the mass loss rate, or it can go into increasing the velocity. So if it's not going into the MLR because of this sublinear relationship, then it should go into the velocity. So then it is accelerating the wind, right? And if that is true, then we should see, if we correlate the mass loss rate with the expansion velocity, we should see that there is an increasing trend. Okay, well, we can do this as well because we calculated mass loss rate and we estimated the expansion velocities. Et voila. There is a correlation between the mass loss rate and expansion.
Good question. Can we not know any of these, even a simpler toy one, theoretically, what could be the correlations between these different quantities?
We do. The problem is, again, that the parameter space is so large that you would have to incorporate, so without a grid of models, right, or something that can produce a bespoke model for any combination, it's difficult to know what the range is going to be. And the difference in systematic uncertainties in various models is so large. It's like 1.5 orders of magnitude. That there are models, and models for this have existed since the late 80s, right? There is a very famous paper from the early 90s, Vasiliadis and Wood, which has, in fact, so this is a mass loss rate versus expansion velocity. They have mass loss rate versus period, and there is a plot, but then you look at it, and it has this much, even in the models, that much uncertainty. And then you compare it to the data, there is nothing, because again, the data was sparse at the time. So first of all, you need a large data set of this sort in order to even see anything. So we're just only now kind of the detailed modeling. The problem is you need to flip a lot of switches there, turn a lot of knobs. So we're still at the kind of boundary of where we're getting to, hey, how can I do this in the semi-order? We need something of that sort in order to do this. Okay, so there is a correlation between the mass loss rate and the expansion. Okay, but the mass loss rate was derived from an equation that has v to the alpha in it. So why is it surprising that there should be a correlation? In fact, if MLR is proportional to v to the alpha or something from that non-steady equation that I showed before, then this slope should be close to alpha. It's not. It's not even close to alpha. It's way different from what alpha is. I think alpha is about 0.8 or something, and this is about 2.3 or so. So this effect is much stronger than what is only due to the mass loss rate, and it's a very strong effect. We did a t-test to determine whether the slope is significantly different from what it would have to be, and yeah, the p-value is extremely low. So this is a true effect. There is an actual correlation between the mass loss rate and the expansion. And yeah, like I said, this has been shown with the mass loss rate versus period as well. Okay, so I'll conclude with the heterodyne results and then very quickly show you a few images. We have 485 stars for which we have detections in 2 to 1 and 3 to 2 CO. And there's a relatively high detection rate, 80-ish% in both lines, significantly higher than what the literature has produced. Many sources have no previously published data, and we do a very good job of representing the lowest mass loss rate sources. So this demonstrates the advantages of a homogeneous volume limited way sample and probing the largest range of mass loss rates. Majority of them have soft parabola profiles, which means that they are probably spherically symmetric wings, but we have a handful of double wing sources and a handful of asymmetric sources of wings as well. We estimated isotopic ratios, but there's still work to be done because of the optical depth issue. Our mass loss rates are consistent despite the large uncertainty in the mass loss rate. They're consistent with what is available in literature. The relationship is a broken parallel. This is not something that was not known previously, but we just have a large enough sample that we can confirm that this happens. The gas to dust, this is the most interesting, in my opinion, in this result, is that despite the fact that the MLR and DPR are used to derive the gas to dust ratio, the gas to dust ratio only anti-correlates with the dust reduction. It does not correlate with mass loss rate. And this could be, this could point to maybe there's wind acceleration, at least at the lower mass loss rates. And this is supported by the fact that there is a strong correlation between mass loss rate and the expansion. Okay, so then I'll show you a few images before I quit. Won't take very long. This is data from other surveys that we have ongoing. That work is ongoing on analyzing these. So first we have. So I'm going to show you some images that talk about the that demonstrate the fact that many of these sources, nearby sources, have. You can see the extension. The actual. You can see the spread in the surface tension problems. So I'll first show you images from the Nobayama data, and then our ACA, which Alfonso has been working on, and finally a teaser from LMD data. So this is the NRO data. That's the beam temperature as a function of distance from the star in astronomical units. So the surface of an AGB star is typically 3 or 5 AU or so. At about 10 times that distance, approximately, you have the dust formation zone, maybe 5 to 10 times the distance. And then at about 1,000 to 10,000 times that distance, you have the edge of the surface shell. So this is relatively close to what one would consider where the CO starts to photo-dissociate. Okay, so what we have here is the black is the NRO data, the gray dashed is the JCMT data. That's 3 to 2. So this is 1 to 0. So this is a known thing. The 1 to 0 transition requires cooler temperatures, exchange temperatures, so it probes larger physical scales. So this is not surprising, the fact that this profile is narrower. This is JCMT 850 micron data. So this is dust continuum and dust continuum data as well. So you can see that the extension is relatively consistent with the dust, the extent of the dust envelope as well. In this case, in the case of IKTAP. In some other cases, not so much. So Nobayama is still more extended than the 3 to 2, but you can see that the dust actually is much brighter at this source. In this case, it's flipped around. CWVO, the dust extension is not as much as the NRO. So the NRO is seeing significant extensions in the 1 to 0 transition. We had 2 undergrad theses that we co-supervised, myself and Alfonso, this year. Again, it's about Pares. So I'm going to show you a couple of images from those. This is for ALMA ACA data. Yeah, looking at 2 to 1 and 3 to 2 with ALMA. So what Joshua did was to use the PSFs and subtract, compute radial profiles and subtract the PSF. And you can see again, there is a significant extension in 3 to 2, 12 CO 3 to 2, and 12 CO 2 to 1 as well. And again, the 2 to 1 is slightly more extended. In this example, more extended. Again, because it requires cooler excitation temperatures to control distances slightly further. So what he then done is calculated envelope sizes for each source, for each transition, and and you can see that they're relatively consistent with each other. So 10 to the 4 AU or so, and that is actually relatively close to where we expect the actual edge of the surface to show. And the fraction of sources in the sample that have extended shells is significant. It's in the 12-0 transitions, it's more than 50% close to next year. And you can do this again. This is, I think, it's really cool. You can plot the extent in one line versus another. So again, the 3:2 versus 2:1. This is the 1:1 agreement, and you can see here that the fact that 2:1 is more extended than 3:2 is generally true. It's not just true for this one source, but yes, it's typical. So this is good. This is what we expect, and that's what we get. So you can see that here as well. Oh, and then Miguel, the other student, what he did was he used MCMC to compute soft parabola fits to the ALMA ACA data. So again, that's the distribution of velocities he gets. These are consistent with what we find in the JCMT data. And then this, so the CO line luminosity is a proxy for the mass loss rate. We didn't want to calculate the mass loss rate from the Randstad equation because of all the uncertainties, but you can still see that there is this trend, and then maybe there's a flattening here, I'm not sure. But there is definitely a rising trend with the mass loss rate with velocity. Finally, so these LNT images, despite the fact that we had issues having them observed in the mode that we wanted, these images are still very promising. If we need time to go analyze them. UANT especially, the source has a detached shell, so it's very nice to see that it's beautifully represented in the LNT data. So one of the talks at the SDSCI spring meeting mentioned that WHydra has a dynamic hotspot, and I'm not showing the image here, but we have a WHydra image as well in the LNT, and I think maybe there's a spot right where Mariam said there was one in their data, so we'll just have to go check that out. We don't have the time. Problems with lots of data, not enough people. So anyone, if you're interested, if you had experience in any of these data sets and would like to help out, please do so. So yes, the last thing I want to do is just a 30-second plug for an upcoming package. It's called Napoli, the Neural Accelerated Posterior Learning Interface. And this is basically anyone who has a grid of model spectra. Doesn't matter what source, what system it's for, AGB, AGN, or GRB, as long as it's a grid of spectra, and as long as each is tagged with the parameters, you can convert that. You can use neural networks to learn the dependence of the spectrum on the parameters, and then use that to perform NCMC fitting, like what was done. So basically, instead of just the cheap quadrado, you are able to generate MCMC fits that give you the actual posterior uncertainties in each parameter and correlations with the parameters as well. So this is fresh. It's not yet fully alive, but it'll be alive next week. So yeah, if you're interested in this, let's talk about doing something with it. Okay, I will end there. Just barely enough. Okay, thank you very much.
Yes, time for questions.
Thanks for your time. I'm wondering if it's possible that we can find new AGB candidates using other infrared survey as WISE or Spitzer.
We've included WISE.
Okay.
Yeah. So in the galaxy, there's not a lot of Spitzer data on AGB stars, especially for nearby because they're very bright. WISE definitely is a very good, very useful resource. But we've already incorporated WISE. One of the again problems is that in the W1 and W2, these sources are basically saturated. So there is I forget CatWise and before that Unwise. These two sources, I think what was done is they somehow accounted for the saturation and corrected it. But even then, the W1 and W2 is basically missing for these objects. So it becomes difficult to use it only the WISE data to identify new candidates. One survey that has existed for a while that we haven't used very much is MSX. So actually, one of the problems with IRAS is there is this strip that IRAS could not observe in the sky. And MSX actually has quite a bit of observations in that region. So one of the things Alfonso is doing for an upcoming paper is first take the overlap region, find out if what the properties are, and use that to derive candidates in the. And I think he already has candidates. So MSX is a very promising thing for this.
Yeah, so I have a couple of questions. The first one is regarding one of your slides towards the beginning of the talk, where you showed calculation to get the mass loss rate that you mentioned didn't work very well for high values. I don't know if I understood correctly, but I think that one. That you could benefit from using ray tracing. I wanted to know how that would work, or what is RT here?
What is, sorry, which one?
RT in the
radiative transfer.
Radiative transfer.
Yes. So of course, if you do radiative transfer, then you don't need this formula, but radiative transfer is time to time. So these are all just shortcuts to apply without using computation.
Okay, and the other one is regarding a couple of histograms you had towards the end of the talk. I wanted to know how did you select the binning? I mean, based on how many data, what was the sample size? How did you select the binning?
Good question. Well, the thing is, you don't even need the histogram. That's why you have these curves here. These curves are the kernel density estimates. So the kernel density estimate does not, so you can, for the binning as well as for the bandwidth of the kernel density, you can do cross-validation. So cross-validation means that you no longer have to choose stuff manually. It just picks the best possible thing to represent your data. The kernel density estimate is basically a much better way of doing estimations of the density. The histogram is just there for people who are familiar with what a histogram is, right, in the background. But you don't have to look at it. The kernel density is what, that represents the best we can do with cross-validation and with density estimation.
We have a question on Zoom from Will. Go ahead, Will.
Okay, very nice talk, Sundar. Thank you. I actually have 4 questions, but I couldn't raise 4 hands in Zoom. So, am I allowed to ask 4 questions?
They're quick ones, yes.
Okay, right. So those are soft parabolas you talked about. So I think you mentioned that soft parabolas include the rectangular profiles. Is that right?
Yes. So the range of betas that you can have, it goes all the way from the most optically thin sources have double horn profile, and then the intermediate rectangular profile.
Yeah, because everything I know about this is what's in Mihalis's textbook. But so you have masering in the low mass loss rate. Is that right? That gives the double horned.
No, so those are 2 different things. So maser profiles can also be double horn, but these ones are about carbon monoxide. So you can also have this. The double horn basically comes in due to a combination of low optical depth and geometric effects.
Okay.
I can send you the reference for this derivation as well.
Okay, no, that's a problem. Okay, second question, a gas to dust ratio. But it seems to me that your gas to dust ratios is larger than in the ISM. But you're saying that most of the dust in the ISM comes from these sources. So I'm wondering how to reconcile that. Does that mean that there's a lot of grain growth inside molecular clouds, which means that you have a lower gas to dust ratio or higher dust to gas ratio in the ISM?
Yeah, so that's a good question. It's a known fact that the gas to dust ratio in AGB stars is very, very different from what is assumed for the ISM. So I know the ISM people typically assume 50 or 100, but the kind of canonical value for the gas to dust ratio in AGB stars is about 200 or so. And it does have a lot to do with the fact that there may be dust formation, dust growth in the ISM.
Right. But it's not like forming new dust particles, it's just getting mantles on existing dust grains. Is that the idea?
Yeah.
Okay. So third question, you mentioned super winds, right? But you seem to be seeing like the mass loss rate topping out at
Yeah.
5 times 10 to the minus 6, but that's not a super wind. I mean, super winds have to be like 10 to the minus 4, right?
Yeah, so yes, there's issues with this that we think it could be super wind because the velocities at which this is happening, about 17 to 20, is where Vasiliadis and Wood and other people say the super wind should be happening. But yes,
Right.
we are aware that the saturation level that we get is much lower.
Yeah. Because I mean, super
Yes.
winds like have to like produce the the envelope that gets ionized in a planetary nebula over a very short time scale of less than 1,000 years or whatever.
Yeah, so
Okay.
we are about so it's not terrible. We are about an order of magnitude off. So our highest mass loss rates are somewhere around a few times 10 to the minus 5, which is within an order of magnitude of the in this stuff, an order of magnitude is totally acceptable.
Okay, right. And so the last question about the wind velocity, that you said there was a correlation between the wind velocity and the mass loss rate. But I mean, I know more about line-driven winds, and there, the wind velocity mainly correlates with the escape velocity of the photosphere. But I guess, is that not the case then for these dust-driven winds because of a more extended acceleration zone?
Yeah, partly that, and also because again, so I'm not entirely clear on. So this velocity that we're measuring is from the gas, and so the drift velocity is different from this expansion velocity as well. And I think that ends up fitting in this. I'm not clear on how the exact translation.
Do you have estimates of the escape velocity, or is it that you can't really define a surface and therefore there's not meaningful?
No, that would require something like radiative transfer.
Yeah. Okay, right then. Very nice talk. Thank you again.
Okay, any last questions, quick questions before we close it? No?
I think Jesus had a question. I'm not sure.
I did, but Will already asked it, so.
Oh, perfect.
All right, let's end here. Thanks, Sundar, again.
Thank you.
Please.